Hello everyone, and I hope you enjoyed my last video on the fairy carousel. I was watching television last night and there was this film on called Interstellar. Interstellar was a space film, it was a science fiction film. But like all great science fiction films, they have to be grounded in rock solid logic. You can't have a film director or a film screenwriter inventing their own physics because it simply wouldn't work and it would have no credibility whatsoever. Nobody would watch it and the film would become a flop. But Interstellar was grounded in rock solid logic, even though the premises seemed to be incredible. One of the themes we discussed was time dilation. Now we know time dilation is a fact because we've verified it experimentally, and also Einstein said so, and that's good enough for most people. What's time dilation? At one point in the film, they were looking for a different planet to live in, so they investigated this Miller's planet, and this Miller's planet was close to a black hole, and they all knew beforehand if you go to this planet, extreme time dilation would be in operation. In fact, if you go to Miller's planet for 1 hour, that's equivalent to 7 years on Earth. If you go to Miller's planet for 5 hours, that's equivalent to 35 years on Earth. So if you go there when you're 20, say, you stay there for 5 hours, you go back to the solar system where Earth is, you'll have aged by 5 hours because that's all the time you're away for. However, when you get back to Earth, everybody else, they won't be 5 years older, they'll be 35 years older, so you'll be a relatively young person. This is allowed by Einstein's theories of relativity, general and special. Now that's a factor of over 60,000. It means time on Earth passes 60,000 times quicker than that on Miller planet. Now that's extreme time dilation. That was perhaps necessary for the dramatic necessities of the film, and we can live with that, that's no problem. How would it be? How would it feel like living on a planet where time dilation was so great? We wouldn't notice. As indicated by the film, nobody noticed anything different. However, what would be interesting though is if we could see each other's planets. That would be interesting. Suppose, for example, there was a 90-minute football match in both planets, and both of these matches were recorded on a mobile phone, and the mobile phone was sent to Earth. One mobile phone was sent to Earth, and one mobile phone was sent to Miller's planet, close to the black hole. And the people on these two different planets observed the match. They wouldn't notice any difference. They wouldn't notice any difference. Because even though they were filmed in one time frame, they're viewed back in another time frame, and that would just cancel each other out. That wouldn't tell us anything. No, we've got to see it from the point of view of, we've got to see one planet from the point of view of another planet. So if we had two telescopes, one telescope on Earth looking at Miller's planet, and the other telescope on Miller's planet looking at Earth, and we're watching a 90-minute football match. Well, if we were on Earth watching the match on Miller's planet, the match would take 10.5 years to complete. So if we start watching it at 20, we're 30 by the time the referee blows the final whistle. Everything would seem to be in slow motion. Similarly, if we're on Miller's planet looking at Earth, the whole match would be over in less than 1/10 of a second. So you picked out your cup of tea, you're about to watch this match. By the time you get the cup of tea to here, the match is over, and everything on Earth seems to be moving quicker. That's the only way you would notice. And I suppose a film director, a science fiction writer, have got the license to play with these things as much as they like. The foundations, the logical foundations are there. Time dilation also is observed for moving vehicles, provided the vehicle is moving fast enough. Einstein's theories predict this. When I say fast enough, we need a spacecraft travelling very, very close to the speed of light before we would observe the effect, even though the effect would also be in operation at much, much slower speeds, but very hard to detect. Now, so suppose you've got an observer at a who's stationary at a bus stop. This observer can see a spacecraft passing by close to the speed of light, and the person in the spacecraft holds up a clock like this. The person at the bus stop will observe the clock hands going slower, and all processes inside the spacecraft going slower, and as the spacecraft is large enough, you would see a football match going slower. But here's the conundrum, and this is the paradox, we sometimes call it. Both situations are equivalent. So, if a person can see a spacecraft passing by at close to the speed of light, someone in the spacecraft will see a stationary observer passing by at close to the speed of light. In this respect, the situation for both observers is equivalent. Meaning, if they both held up a clock, the stationary observer would see the clock in the spacecraft going slower, and at the same time, a person in the spacecraft would see the stationary observer's clock going slower. Both situations are equivalent, so both would see each other in slow motion. This gives rise to the famous twin paradox. Suppose Janet and John are twins and they're both 10 years of age. Janet jumps in a spacecraft. The spacecraft is now passing by John at a speed close to the speed of light. Both children hold up a clock for each other. Janet sees John's clock going slow, John sees Janet's clock going slow. This means John thinks time is dilated in Janet's spaceship, and Janet thinks time has been dilated back home on Earth where John is. So, when the journey's over and Janet steps out the spacecraft, the twins will be thinking different things. John will be thinking, well, since Janet has experienced time dilation, she won't have aged at the same rate as I have. So she will be younger than me. But Janet will think, John has not aged at the same rate as she has, so he will be younger than me. Both twins think they're going to be older than each other. Only one can be correct though, and the paradox has been resolved, and Janet is correct. She will be the one whose life has been on hold while John has aged at normal Earth rate. And that's the key here. Janet hasn't benefited in any way, and she's not lost out in any way either. John has lived 10 years and he's now 20, and he's finished school and he's now on his way to about to start his new career. Janet is still an 11-year-old girl. She's yet to do this. In that respect, nobody benefits from the life being on hold. Although, you could ask, suppose you had the opportunity to go to a planet for a year, say, close to a black hole, or go on a spacecraft for a year. And when you came back to Earth, say, depending on the time factors involved, the time dilation factors involved, I should say, time has advanced, say, by 60 years. Who would choose to do that? Well, that's an interesting question, and it shall be the topic of my next video. Thanks for watching the Young Scottish Physicist.
To the left. With your hands on your hips.